So in this next section, we're going to look at reactions that alcohols can undergo. And there's a couple of reactions that alcohols can undergo. So there's combustion reactions, there are oxidation reactions, and then there are dehydration reactions. We're going to specifically focusing on the combustion reaction first because there's quite a big sort of theory and practical component to it, and also some calculation questions that we need to do as part of that. Right, so it's the heat of combustion prac, and you would have done something similar in year 11, hopefully. But we're just going to revisit that prac again and learn it from scratch, so we make sure we cover all the major details with that prac. Okay, so the combustion of alcohols, and in particular the combustion of ethanol is what we're going to focus on, but it can be the combustion of any alcohol really, is essentially the same as any other combustion reaction. So fuel plus oxygen gives you carbon dioxide and water, right? You're assuming it's a complete combustion reaction. So you might have something like C2H5OH, which is ethanol, and that'd be liquid or could be aqueous form, all right? And then plus 3O2, which is a gas, goes to form 2CO2 plus 3H2O, okay? So that's what the balanced equation would look like. And obviously, like I said, you can generalize this with any alcohol. So you can change it to like propanol, butanol, etc. Okay, it doesn't have to be ethanol, but that's what we're going to focus on for this prac. Now, the thing is, when you're balancing these equations, it might seem like a very small point, but just don't forget that there's an oxygen in the actual alcohol itself. And then there's also a hydrogen. So whenever you're balancing equations, you can easily make the mistake of just worrying about the oxygens in the oxygen gas molecule, but there's also an oxygen in the actual fuel itself. So just keep that in mind, okay? Now, when we talk about heat of combustion, the molar heat of combustion of any substance is the amount of energy that you release when you burn 1 mole of that substance, or more, to be more technically correct, when 1 mole of that substance undergoes complete combustion with oxygen, okay? So it's the amount of energy, say for example, if we're calculating the heat of combustion for ethanol, it's the amount of energy that 1 mole of ethanol will release if it undergoes complete combustion, okay, with oxygen. So that's what we're measuring, the delta H of the reaction, and they've got the equation for you there. It's the enthalpy content of the product minus enthalpy content of the reactants. It's very difficult to measure the absolute enthalpy content of a product or of the reactant, but it's easier. It's still not easy, but it's easier for us to measure the change in enthalpy, because that's the energy released, and we can measure the energy released from that reaction. And this is how we do it. So this is what a molar heat of combustion setup might look like. Very, very standard setup at school. So you've got your tripod, you've got your thermometer, your beaker full of water, and your gauze mat. And then you've got your spirit burner. Very, very important. It's not a Bunsen burner, because you want to test different fuels. And if you plugged your Bunsen burner in, you would be testing the heat of combustion for the fuel in that Bunsen burner, whatever the fuel your school uses. So it could be like ethane or propane or something like that. But you can't actually change that fuel. So that's why we use these things called spirit burners, which is literally like a burner where there's fuel in it. It's detached from the main gas main. It's just like a contraption where you've got the fuel in the container here, and then you just set it alight and it burns that fuel, right? So we're testing the heat of combustion for ethanol. Obviously, you can have different spirit burners with different fuels in them, okay? So that's the experimental setup. And before we move into the calculations, with the heat of combustion, we're trying to measure this, right? We're trying to measure the amount of energy released. Right, from this combustion reaction, right? The combustion of ethanol, right? That's why it's a heat of combustion. But the problem is, it's not like the temperature we just stick a thermometer in, right? There's no contraption or no device out there that can measure directly the amount of energy released from this reaction. So what we do is we measure this, right? We measure the temperature change in the water, and then we correlate that with the amount of energy released from the reaction. So what we're saying is, yes, this reaction is going to release energy, and mostly in the form of heat, but we can't measure that. But that heat that this reaction releases is going to go, we assume it's going to go directly into this water and heat that water up. And so we're going to use a calculation here, namely the Q equals MC triangle T calculation, to find out, well, given that water increases by a certain amount of degrees, that's going to correlate with the amount of energy that's released directly from this reaction, right? So the main idea is we're trying to measure this, but we can't. So we instead say, assume all the energy that's released from this reaction goes all into this water, and then we'll measure this water instead, okay? And hopefully those numbers should correlate. And obviously there are assumptions that we've made, and we'll discuss those in a sec, okay? So if we have a look at the question down here, and it says, we want to calculate the molar heat of combustion for ethanol with the data given, okay? So just remembering back to year 11, the molar heat of combustion reaction, we first got to find Q, and Q, think of that as the heat absorbed or the energy absorbed. It could also be the energy released, it doesn't really matter. But for this example and for all heat of combustion examples, just to assume Q is the heat absorbed. And so what is Q measuring? It's the heat absorbed for this setup here, right? For this beaker of water here, right? So we're saying that the amount of heat absorbed by that beaker of water is equal to the mass of the water that's present, times it by the heat capacity of water, times it by the temperature change of that water, okay? So if we can find the mass of the water, the heat capacity of water, and then find the temperature change of that water, and times them all together, that will correlate with the amount of heat that water has absorbed, right? So the amount of heat that this water here has absorbed. So how do we do that? Well, we need the mass of the water. The mass of the water is 250 grams, so that's our M, right? That's going to be our M. The heat capacity of water, our C, is 4.18, and we get that from the data sheet, so 4.18. And then, so our temperature change is going to be 59 minus 19, which is going to give us 40, and it should be 40 degrees Kelvin to be technically correct, okay? So really, you have to convert these to Kelvin and then calculate the difference, but you'll get the same number either way, okay? So we've got all our data for the Q, right? So so that's going to be 250 grams times 4.18 times 40, like so, okay? And just make sure when you do these calculations, always have the things in the same unit. So if you're going to use grams here, that's going to be 4.18, and that's going to be degrees Kelvin, yeah? And so if you plug that into the calculator, what are you going to get? Well, it's going to be 418000, okay? So that's 418000. All right, so therefore Q equals 418000, and the units for this are going to be in joules, which means that's also equal to 41.8 sort of kilojoules. All right. So what this is saying is, given a mass of 250 grams of water and a heat capacity of 4.18 and a change in temperature of 40, for this to all have happened, water would have had to absorb 41.8 kilojoules of energy, right? And where does that 41.8 kilojoules of energy come from? We assume it all comes from this ethanol here. So we'll talk about that in a sec. But just to sort of clarify some things in this formula here, Q equals MC triangle T. So this formula here, it's the same as the one we've used down here, right? The mass is the mass of the water, not of the spirit burner, or the amount of ethanol that you've used. So that's a very key mistake that students can make. It's the mass of the water that's getting heated up. What heat capacity means is it's the amount of energy required to increase 1 gram of the substance by 1 degree Kelvin, okay? So the heat capacity of water is 4.18. So what that 4.18 means, it means to increase 1 gram of water by 1 degree Kelvin, you need 4.18 joules of energy. Right? That's what heat capacity means. So water's quite high because water's a bit of an insulator. That's why you need a lot of energy to increase 1 gram of water by 1 degree Kelvin, right? And it's going to change depending on the material you use. Okay, so that's what the C means. And then the delta H, which is your change in temperature, right? That's quite straightforward. You just measure it from the thermometer, right? So we plug that all in and we get that Q here. It was 41.8. And we're saying, okay, in order to heat water up by 40 degrees, given that we've got 250 grams of water and given that heat capacity of water is 4.18, we need 41.8 kilojoules of energy. Where do we assume all that energy comes from? Well, we assume all the energy that the water absorbed comes from the energy released from this combustion reaction of ethanol. So that's an assumption that we should always write down in an exam. So assume all heat or energy absorbed by water is equal to the energy or the heat released by the combustion reaction, all right, by ethanol combustion. Right, so we're assuming that all the energy released by this reaction has gone into heating up this water. Okay, and we'll talk about this assumption in a sec because it's not the correct assumption to make, but that's the assumption we need to make to do the calculation. So we assume all the energy absorbed by the water, by the H2O, okay, is equal to the heat or energy released by the ethanol combustion reaction. So then we can do our delta H calculation, right? So our delta H calculation, so to find the heat of combustion, right, delta H subscript C, right, to denote heat of combustion, that's equal to Q divided by N. So it's the total amount of energy that you've released divided by the number of moles of ethanol that you've burned, right? So how do we find the number? So we've got Q, right? That's the amount of energy we measured that the water absorbed, and we assume that's equal to the amount of energy released by the combustion reaction. But how many moles of ethanol do we burn, right? So how do we do that? Well, we come back up here, and then you look at the mass of the ethanol that you used, and that would be the initial mass minus the final mass, okay? So the mass of ethanol, okay, the mass of ethanol is actually equal to the difference between these two, which is going to be, if you plug it into calculator, 2.3 grams, right? It's going to be 221.4 minus 219.1, okay? So you're going to use 2.3 grams of methanol. So because we use 2.3 grams of methanol, I'm just going to change this bit to black, just so we can distinguish between the two different types of calculations. So now so the bit in blue, we're doing the calculation for up here. The bit in red, we're doing the calculation for down here, right? So we assume the amount of heat released from the ethanol combustion was equal to the amount of heat absorbed by the water. So we've got Q, we said N, we need to find the number of moles of ethanol, C2H5OH. The number of moles of ethanol is equal to the mass, which was 2.3, divided by the molar mass of ethanol. And the molar mass of ethanol is going to be 2 times 12.01 plus 5 times 1.008 plus 16, right? And so if you plug all that in, plug it into your calculator, you should get approximately 0.05 moles, okay? So you should get approximately 0.05 moles. Now, once we've got all that, then we can plug it into this equation here, because we've got the number of moles and we've got our Q. And so therefore, our final answer, therefore the delta H, or the heat of combustion for ethanol, is going to be 41.8 kilojoules divided by 0.05 moles. So our final answer is going to be 836 kilojoules per mole. Like so, and then we've just rounded it to 3 SF. Okay, so 836 kilojoules per mole to 3 SF. Right. So to recap what we've done, we've said, okay, we can't measure this, so we're going to measure this, right? We're going to measure how much temperature the water increases by. And so we've measured how much the water temperature increased by. We plugged it into this formula, and that will give us the amount of heat absorbed for water, right? Given that amount of water, given 250 grams of water, it will tell us how much heat that has absorbed, given that temperature change. And then we assumed that this bit in here in blue, the amount of energy absorbed by the water was equal to the amount of energy actually released by the combustion reaction, okay? And so the amount of energy absorbed here, we just carried it over and said that's the amount of energy released by this reaction here. Then we had the amount of energy, the total amount of energy released by this reaction, but then we had to find out, because heat of combustion is the energy released per mole, we had to find out how much energy was released per mole. So we found the total amount of ethanol we used in mass, then we converted to moles, right? Converted to moles. Then we did our delta C calculation, which was the amount of energy released divided by the total number of moles. So Q on N, and then that's the number that we got there, okay? 836 kilojoules per mole. And what you should be doing in the exam is in chucking a negative sign, because it's an exothermic reaction. So exothermic reactions always release energy, so it's a negative sign. Now, there's a couple of things to this calculation that you need to worry about, because different schools do it differently. So you've just got to be very wary of how your school wants you to set out the working. For the HSC, they're very, very lenient on this, but for schools, they can be quite strict.